Hello, class. Here's an overview of Module 7, Lesson 4. Well, just like with the third lesson in this module, in my overview video, I'm going to discuss the hypothesis test in this lesson, and then you can work through the Canvas pages to practice the R commands. Okay, well, in this lesson, we are discussing hypothesis tests for population proportion. We will discuss, well, the difference between an exact test and an asymptotic test here. The objectives: conduct a one sample and two sample z-test for population proportions in R. We want to conduct the exact binomial test for one sample proportion in R, and then really just distinguish between when you use each test. Okay, now that I have discussed the objectives, let us move into discussing the hypothesis tests. So we consider hypothesis test for population proportion, and this means, maybe I'll put a little line here. We have both a one-sided and two-sided test. We have both one sample test and two sample tests. So first, let's discuss a hypothesis test for one population proportion, and this is what's called a z-test. So if we want to show the proportion P of a certain type A and a population is not P0, well, our null hypothesis is right here, H0, P equals P0, and in this case, the alternative is that P is not equal to P0. This will be a two-sided test here. If we have a random sample of size n, suppose we have x, so this is a number, x of the n that are of type A. X, well, it's a binomial random variable with size equal to n and some probability p. If we want to estimate p from our sample, the point estimator is this p hat, which is x over n. It's just the proportion of this type A in our sample. Now, under the null hypothesis, and this is an important part here, if we are working with the assumption that p equals p0, and also using the central limit theorem, which means n needs to be sufficiently large, then the sampling distribution of this p hat is approximately normal with mean p0, and here's the standard deviation. This, well, really follows from things we have discussed before. Therefore, okay, with this null hypothesis, p equals p0, and alternative hypothesis, p is not equal to p0, we will reject the null provided this z statistic is either less than the alpha over 2 quantile or greater than the 1 minus alpha over 2 quantile. This would be with the alpha level significance test. So this, maybe I'll write that, z sub alpha over 2 and z sub 1 minus alpha over 2. These are our quantiles. Now let's do an example here. I'm going to say this is by hand, although I'm really going to use R, but by hand means I'm going to physically calculate this z statistic rather than use a pre-programmed test in R. Okay, so first, before we get started, let's read what the example is. We have an experiment crossing flowers of two genotypes, and then we have this recessive progeny with white flowers and this dominant with purple flowers. We want to test if the crossing is random, which would say 1/4 are recessive, 3/4 are dominant. Now, here, this P is the proportion of purple flowers here. All right, so the 4 steps of hypothesis testing. Number 1, we write down a null hypothesis and alternative hypothesis. Here, the null hypothesis is that p equals 3/4. Alternative is p not equal to 3/4. Okay, step 2 of hypothesis testing. We collect data So we have empirical data from 900 plants. 625 have purple flowers, 275 have white flowers. Step 3 of hypothesis testing was to calculate a p-value. Okay, well, what we're going to use is exactly this. So our p-hat is 625 over 900. P0 is 3 over 4, and then n, 900. Okay, but we will do this in R for ease of calculation. My p-hat, 625 over 900, and we can see, I will write this down, that p-hat, which was 625 over 900, this is approximately 0.694. Now, we can also tell R what P0 is. Maybe I'll write this down. P0 equals 0.75. And then what we want is this Z statistic. So I have taken p-hat minus p0 over, well, the square root of this using n equals 900. And what do we get here? Let's write it. Our Z observed is minus 3.85. Now, this is negative, so what we want 2 times, well, this is capital F of minus 3.85, which is the probability that a standard normal random variable is less than or equal to 3.85. The 2 times will get the area in both tails. We are using a two-sided test. So let's figure out what this is. Okay, this is approximately 0.000118. Okay, very nice. Okay, I have just rearranged my work. Now, am I finished with this page? No. Why is that? Well, there are 4 steps of hypothesis testing. The 4th step is to make the conclusion. So number 4, well, we have a very small p-value. So if we're using, say, 0.05, we reject the null. And it seems that the crossing does not appear to be random. Very nice. Well, in R, we may use prop test. That's why I was saying sort of in quotes, I was doing that by hand. Namely, I was actually calculating a Z statistic. We may use prop test in R to get the exact same p-value. In fact, I have that built into our Canvas course. I want to make a remark about confidence intervals and the Z-test for proportion. Now, we discussed how a 100 times 1 minus alpha % confidence interval is equivalent to an alpha level hypothesis test, where we reject the null provided this theta 0 is not in our confidence interval. For a population proportion, in Module 6, Lesson 3, we discussed the confidence interval, and this is really what's called a walled confidence interval, and it looked like this. So we use this estimated standard error, which came from our sample proportion, this p-hat. Okay, however, the Z-test for proportion is based on this statistic. And you notice it's not the same. In fact, the sampling distribution of this sample statistic would not be the same as if we use this estimated standard error. And so rejecting the null does not exactly correspond with P0 not in the walled confidence interval. Okay, in R, this prop test will return a confidence interval, and it's what's called the Wilson confidence interval. It's typically better than the walled. I won't go into the mathematical details, but I will say the idea is that you get a 100 times 1 minus alpha % confidence interval by including all P0, such that H0, the null being P equals P0, is not rejected at level alpha by the z-test. So it's really a remark. There are multiple confidence intervals in general you could use for proportion in statistics. This is two of them, Wald and Wilson, and prop test will give you the Wilson confidence interval. Next, I want to talk about the binomial test. This is an exact test for proportion. So the proportion test that we just discussed, the z-test, is based on an approximate sampling distribution of p hat, this estimator for population proportion. However, we know the exact distribution. Under the null, H0, it's just binomial with size n and probability P0. So we can calculate a probability directly from this binomial distribution. Let me just say that if you have a one-sided test, it's much easier. You can calculate it from the cumulative distribution function of the binomial distribution. If you have a two-sided test, it's a little bit more intricate, but we have R. So that's the wonderful thing here. We have binom.test. It is an exact test. And generally, I am sort of talking about the difference between asymptotic test and exact test right here. An asymptotic test is based on the asymptotic approximated distribution of the test statistic. What that means is the distribution is approximately true for a large sample size. Okay, back up to the first page. You see, I use the central limit theorem. We know that means n must be large. And then I have approximately. So this is an asymptotic test. Okay, come back. And that's exactly what I say here. The z-test is an asymptotic test, really should only be used for large n. An exact test, on the other hand, is based on an exact distribution of the test statistic. The binomial test is an exact test. We will always, I'm going to box this, prefer using an exact test over an asymptotic test. And so the binomial test is going to be a better test in general. It's exact. Sometimes in statistics, though, the exact test may be hard to get or too computationally intensive. But in this situation, the exact test, the binomial test, is almost always preferred. The last test I will give an overview on is when we want to compare two proportions. So here we want to test whether two different proportions are the same. The null hypothesis is that they are the same, and then we have three different possible alternative hypotheses. This one would be a two-sided test, and these two would give one-sided tests. Well, suppose we have two independent random samples of size n1 and n2, and we have this point estimator, p1 hat and p2 hat. Here, x1 would be the number of certain type out of the n1, and x2 would be the number of the certain type out of the n2 when the sample sizes are large. So this is an asymptotic test here. The approximate sampling distribution of p1 hat minus p2 hat is normal, with mean p1 minus p2 and this standard deviation. We have a z-test statistic where we use a pooled variance. So this is in the same spirit as when we were comparing two population means. Under H0, the sampling distribution of this test statistic is approximately normal, mean 0, standard deviation 1, so standard normal distribution. So this is just an overview of this two proportions comparison. Almost always, this is the better way or best way to actually calculate is using prop test. Well, this is all I'm going to discuss in our overview. Really, I just wanted to give an introduction to these tests, and we did one example. At this point, you should work through the R scripts in our Canvas course. Thank you so much, class.